Please welcome Lea Becker, BMW Foundation, Herbert Quandt.
All right, so the next invention that I bring to you is technically invisible. It's syngas, and I myself didn't know before meeting the startup what syngas was. And then I learned it's a major compound of the chemical industry. And usually it's made, again, from fossil fuels. But the startup that I'm introducing now has found a way to make it out of plastic waste. And in that way, they're taking, again, one of the things that we have way too much of, and they're turning it into a valuable compound for the chemical industry. I feel like that's kind of the theme today, really. What's more to know about them, is that they already have a running facility where they're testing a bunch of different input materials. They're even testing if they can take shoes or shredded car parts. And next year, they're going to have a running facility in a chemistry park. Without further ado, Maike from Cyclize.
Breaking the wall to circular plastic and CO2 recycling. Maike Lambarth. Cyclize.
One is pretty obvious, it's the growing amount of plastic waste. The second one is invisible, that's the growing amount of CO2 in the atmosphere. We ended up here by discovering fossils and using them. Turning fossils into basic materials emits CO2. One of those basic building blocks is syngas, a mixture of carbon monoxide and hydrogen, and used for basic chemicals. Basic chemicals we need for 95% of all industrial products, and products that we know from our daily lives are plastics, colors, foam like the comfortable chair you're sitting at, electronics, pharmaceuticals, hydrogen, fertilizer, fuels, and many, many more. Reaching end of lifetime, those products get mainly incinerated or landfilled, causing 15% of the global industrial CO2 emissions. Today, only 9% gets recycled, but why is that so difficult? Well, most of the product contains of many different molecules, so it's hard to separate or to use them, even using technologies like pyrolysis or depolymerization. Cyclize has developed a recycling technology that recycles on the molecule level, converting waste, any kind of waste, the waste of the waste, together with CO2 into syngas, this basic building block where you can start the journey all over again. The game-changing part that Cyclize has invented is called non-thermal plasma, a robust but gently molecule chipper. The demand of syngas is growing from year to year, and to reach net zero, we will need further technologies in addition to electrolysis or CCS according to European scenarios. Of course, the biggest demand won't be addressed by those. In 2033, the global syngas market will crack the 100 billion euros line with 10 billion in Europe. So Cyclize will cover 1.5% with operating plants in Europe and in addition a licensing model to scale globally. The business model is to take 1 kilogram of waste, get paid for that, add 2 kilograms of CO2, and produce 2,000 liters of syngas, which we sell to chemical companies. Of course, 2,000 liters are not enough, so we are building big plants that are producing millions of liters per hour. To produce non-fossil syngas, we have several options, all in similar readiness level. So let's compare the production costs of different available technologies. Biogas reforming is easy, but has high feed costs. Electrolysis plus CO2 has really high energy demand. Thermal waste to syngas technology burns part of the waste to use the released energy, but that is producing CO2. The patented Cyclize process is cost competitive, recycles CO2, and enables circular plastic. This is how plasma looks like. And this is our CTO, he's 170 for scale. In this setup, we are testing our plasma drivers, which we develop on top to the plasma process itself. When we started the company, we had a reactor at this size, applying for exist funding. And even before that, we were researchers at the University of Stuttgart, starting from scratch with really small plasma sizes. Today, we have an operating demo plant, and if you want to become fully circular, you can send us your waste and we test your waste. This year we have closed a 5 million oversubscribed seed round to build up the pilot plant in a chemical park, followed by a Series A to build up the first of its kind plant to commercialize and then scale to industrial plant size. So a scaling factor of 200 is waiting for us, but 1,400 we already managed. Together with my fantastic co-founders of engineers, inventors, and entrepreneurs, backpacked by a strong board of experienced investors with the former CTO of Covestro as a chairman, and our fantastic team, which is growing of international and interdisciplinary talents, we are hitting the wall to circular plastics and CO2 recycling. Thank you.
Let's break down that wall. Wonderful. Questions, dear jury? I'm taking them all now. Yes, we have one here. Yeah, David, please.
Just at the scaling up side and your funding round, that doesn't seem very much money you're asking for. I mean, come on. You need to build a pilot plant for the first of a kind. What sort of cost is that going to be?
Well, I mean, it's a mixture of grant financing and equity. So the equity was 5 million. That's closed already. Together with the equity, that will finance the first pilot plant. So that's not a commercial plant size already. It's just to prove that we meet the specifications, and then the Series A will be much higher for sure.
Do you know what that's going to be yet?
Between 15 and 20 million.
Okay.
Okay, next question. Iris?
Thanks, Maike. I was just wondering which polymers you've actually tested so far and whether you can do, for example, also PVC. And on top of that, what kind of pre-treatment, sorting, drying, etc. is needed for this?
Yeah, so we're focusing on waste that I brought some samples here. You can have a look at it. It's shredder fractions from a different waste, so residue waste, for example, or packaging waste that we are testing. And we can use the whole bunch. So PVC is no problem. The plasma is very robust. We have no catalyst in it. The only issue with PVC is that you end up with halogens that are in the syngas, so you need to have a robust plant, so you can't use the common metals, but that's a problem you can solve. The plant will be more expensive, but it's possible. Yeah. So you need Inconel, something like that.
Okay. Next question. Yes, Stefan, please.
You mentioned, you mentioned here. I'm here.
Ah, sorry.
Yeah, no, just,
I'm sorry.
He moved.
So broad.
Yeah, exactly. Exactly. No, you mentioned 4 different types of competitors. Yeah. So one were better on cost, the others on heat, the third on outcome, the third on waste. Which one do you take most seriously? I mean, because they may also change their model and come onto your heels. Which one is the one you fear most, or are you sure that you can actually, because you're very beneficial in all of those 4 factors, you can drive them down further and then therefore grab the market for your own?
Well, I mean, the market is really, really big, so there's enough space for all of us. But when it comes to customer, and we're in the basic chemical industry, right? So their price is really, really important, and they're not very willing to pay a green premium. And our technology, there's no need for a green premium because production costs are so low. So even though biogas, for example, is easy to treat, it's really hard to come down with the costs. And therefore, I think we have a great advantage.
Cool. Next question.
So
Here in the audience and here in the audience.
Just
2 short ones, please.
Do you have an idea how much it is the energy cost that you have associated, for example, to a tons of plastic? And another quick question, if you have.
Yeah.
So we have 3 times less energy requirement compared to electrolysis, and that's a big game changer.
Okay, sorry. Next question. We only have 40
With
seconds.
CO2, you can produce food and other stuff. A key issue is always what level of purity and quality of CO2 do you need for your
Yeah, so for us, the purity really doesn't matter. The only issue is whatever you're going to do with the syngas, you might accept some nitrogen in it or not. So for the plasma itself, it doesn't matter, but typically you use CO2 from point sources and in the future maybe from direct air capture.
Okay, and I think that was the last question. Sorry for interrupting second questions. Thank you very much for all the answers.